All right, everybody, we are now going to move to the first of our mini topics. Remember, I said that we would have some larger topics you were going to be quizzed over, or tested over, like descriptive statistics, correlation, t-test. Well, this is an example of one of the smaller lectures that has information that is still important in it and that you will need to know going forward, but you're not going to have one of the big tests on. And instead, you will have an assignment due over it. And that will be coming up before you take your next test. So this is meant to kind of supplement information from the time you finish the descriptive statistics test and before you move on to the next module. All right, so let's get to it. The normal curve. Well, the first thing we have to talk about is how we visualize data. So when you get a data set such as this one of the most basic ways to visualize it is to make a histogram or a frequency distribution, as you can see at the bottom. And we do this for several reasons. If we don't want to do all the math, this frequency distribution gives us a pretty good idea of what's going on. Just alone from seeing this, you can see that 46 is the one that occurs the most frequently. It seems like they generally clump around there, but it is not perfect where most people are 46, 45, 47. You see maybe 50 is a bit of an outlier there. But nonetheless, this is a pretty good way to start off visualizing data. And if you wanted to, we could draw a estimate of a curve over there. You can see my PowerPoint drawing skills are not perfect, but it's not a perfect curve anyway, so I guess that's all right. So we could use this curve, we could draw this curve as kind of an estimate of what's going on if we wanted to kind of normalize what's happening. Well, we sometimes can't fit in all of the intervals of our data. For example, with salary. In this past one, there were only things that were 40, 41, 42, etc. Well, in this graph, you can see there's 25,000, 50,000, 75,000, and you can't perfectly put every single occurrence of income. So somebody made $75,001 last year. I'm sure there was at least one person. Somebody made 75,002 cents and 3 cents, etc., etc. And we can't possibly put all of those points along an x-axis like we did with this past example. We can't put every one of the millions and millions of possible intervals there. So instead, sometimes what we'll do is we'll draw curves such as this one that will estimate what's going on. Or another way we can do that is by looking at things like normal curves. So a normal curve is just a commonly occurring distribution of numbers. And it turns out that many variables fall along a normal curve distribution. So what is a normal curve? Well, here you can see the kind of standard normal curve. The normal curve, as you can tell here, starts out with a mean at this point, and it goes up in units of standard deviation and down in units of standard deviation. And we'll talk about what this means more practically in a minute. So, some properties of the normal curve. What do you need to know about it? Well, first of all, you might have already noticed it, but it's symmetric around the mean. What that means is that from the mean up, that is the same as the mean down. So we have 34.1%, both one standard deviation above and one standard deviation below the mean. We have from one standard deviation to two standard deviations, 13.6. Well, from -1 to -2, it's 13.6. And from -2 to -3, 2.1, 2 to 3, it's 2.1. So really, and because you're going to want to memorize the percentages on here, you really only have to memorize 4 numbers, and one of them, the last one, is really easy to remember. So if you memorize these 4 numbers, you have memorized those 4 numbers also. So it's symmetric around the mean. Second, it is unimodal, meaning there is one mode. So the most commonly occurring score that occurs is the mean. That is, in a normal distribution, the mean is the score that occurs the most often, which means that the mean and median are equal. Mean and mode are equal, but it turns out the median is also equal. If you have the same number of scores above and below the mean, well, remember going back to how we would calculate the median, You just chop off the scores on the bottom, chop off the scores on the top. It would turn out that the median would be the mean, would be the mode. So they would all be equal. And as I put here, normal curves have the same proportion of scores at particular points in the distribution. So it's not only from the mean to one standard deviation above the mean, there's 34.1% of data, but that's true for all normal distributions. So if you had a normal distribution for height, where you had the mean of height, and you plotted one standard deviation above the mean of height, there is 34.1% of people who would be from the mean to one standard deviation above. If you did it for income, the mean to one standard deviation above, it's 34.1. If you did it for weight, the mean of weight to one standard deviation above would be 34.1. It is true for all of the normal distributions. Okay, so how is it that these normal distributions can be different then? Well, we can see that they can be different by their means and their standard deviations, the values of those. So, in some cases, for example, the Wechsler IQ score, the mean is 100 and a standard deviation is 15. So the mean is 100, a standard deviation above the mean is 115, two standard deviations 130, 3 145, etc. Now for the Stanford Binet, the mean is 100, but the standard deviation is 116. Excuse me, standard deviation is 16, making this 116. That's 16 also, 16 also. Whereas if we look at height, the mean is just under 5'10 for US men, and for OkCupid men, it's slightly taller. Maybe they're over-reporting their height. But nonetheless, the content of these don't matter so much. It doesn't matter that it's IQ and height. What matters is that you can tell that means and standard deviations are really the only way they change. From one standard deviation, from the mean to one standard deviation above the mean in height is the same 34.1% that is from the mean to one standard deviation above in IQ. All right. Now, it is true, at the beginning I said normal curve is a commonly occurring distribution. Not everything is normally distributed. So, this, for example, this is the number of return registrations, so registration on, sometimes you have to register or could register electronic devices or something like that. Well, it turns out if you're going to register it, it's going to be a couple days after getting it, or almost not at all. There are very few people who wait 5 years and then register something. So it's not that perfectly nice bell curve normal distribution that we've been seeing. Similarly over here, the length of stays in hospital after surgery. This, we can see that the mean, median, and mode are not equal, and so we already know it's not normally distributed, but this also doesn't have that bell shape. And this is actually a really good example of a time when, if it were symmetrical around the mean, it wouldn't make any sense. Think about it. Let's pretend that this were the mean, and it tapered off like this. If it were symmetrical along the mean and you had it this way, that would mean some people would have negative days in the hospital. That doesn't even make sense, right? So some things are not normally distributed and some things shouldn't be normally distributed. This makes sense. Okay, so the technical way to talk about this is positive skew and negative skew, or right skew and left skew. So a right skew occurs when there is the tail of the distribution is pulled out to the right. This is also called positive skew. And the way to remember right and positive, if you think of this as a number line, so if this were 0, 1, 2, 3, etc., along the x-axis, positive goes right, negative goes left. So the right skew, or the positive skew, would be one in which the tail is pulled out. And that could be a case where there are outliers or an outlier or something like that that pulls the mean up. And this is exactly what we saw in the descriptive statistics lecture when we saw that if there is a high outlier, the mean will change a lot because the mean is sensitive. The median won't change as much because it's less sensitive to outliers, and the mode is very insensitive to outliers, so it barely changes at all, if at all. So that's what's occurring here. Is there's a positive skew, some outliers, or just a skew to the right pulls the mean up more than the others. And the left is the opposite, left skew or negative skew. The tail is pulled to the left, meaning there are low outliers, there's a low skew, something is going on in the data there, which would mean the mean would be lower, the median would be slightly lower, and the mode would be almost unchanged as a result of these outliers or skew. So you can have some things that are not normally distributed, that should not be normally distributed. You could even have some things that are not normally distributed that maybe they should be. Maybe if somebody screwed up the data and there shouldn't be somebody who has a really high outlier. This can happen, and we're going to see this when we look at SPSS. This can happen when you're coding, and let's say you have a scale that's 1 to 5, and somebody accidentally puts in 55 for one of the scores. They could not, maybe they're not meaning to do it at all, but that could pull up the mean really high, just like the million did in our descriptive statistics outlier. Additionally, to skew, you can have something called kurtosis, and you don't really need to know what this is other than to maybe know the term. Kurtosis is when it talks about how peaked your distribution is. So if you have a high kurtosis, you can see that things are pushed in. So this is really high up in the distribution. Whereas if you have a low kurtosis, it could be a really flat curve. So it typically is not really flat. It's typically more around here. But this can be a case where things are not normally distributed as we would like them to be. For example, if we were to do a normal curve of the number of chromosomes in people's bodies, most people have 46. There are a few people who have 47, 48 even. Some people could have up to one fewer. And so there would be a case where 99% of people are going to have 46 chromosomes, and there are only going to be a couple people off here and nobody on the tail either way. So that would be a time when this is highly kurtotic and therefore not normal. For those of you who have any inclination towards psychological or even physiological testing, this comes up a lot. One of the ways that people can get diagnosed with certain types of clinical abnormalities is by looking and seeing how far they score above or below normal distributions. For example, in Shelby County in Alabama, if you are 2 standard deviations or more below the mean as a preschooler in something, you are entitled to get special services. So my daughter has Down syndrome. If she were 2 standard deviations or more below the mean in some kind of physical, let's say, outcome, she would be entitled to get physical therapy through the state. Other times, it could be looking at depression. There might be a clinical cutoff of 2 or more standard deviations above the mean on a depression scale in order for you to be diagnosed as clinically depressed. Now, how do we draw the curve? Well, this is one formula for it, but it turns out this is way too much for what we're going to do. So let's make it a little simpler, shall we? All you're going to have to do is draw a line, calculate means and standard deviations, and then draw a curve. So let me show you how. So this is a kind of step-by-step. It'll actually be a little easier for me to walk you through it, but you can come back to this slide in order to kind of go step-by-step and see what's happening. So let's say we have calculated something has a mean of 1.6 and a standard deviation of 0.8. Well, what you'll want to do is you'll draw an x-axis, you'll plot the mean, and you'll plot 1, 2, and 3 standard deviations above the mean, and 1, 2, and 3 standard deviations below the mean. The way you get those numbers is you take your mean, and you add the standard deviation. So 1.6 plus 0.8 is 2.4. 2.4 plus 0.8, which is your 1 standard deviation unit, is 3.2. 3.2 plus 0.8 is 4. Conversely, 1.6 minus a standard deviation of 0.8 is 0.8. 0.8 minus 0.8 is 0. And 0 minus 0.8 is negative 0.8. Once you have these points, then we just draw an estimate for the curve. Now, I am not a math professor. I'm sorry. Well, I'm not. I'm an art professor. Also, I'm not very good at drawing, even if I were. So I'm not demanding much of you. What I want is you to draw an estimate of the normal curve. So Something like that. Give it a shot. If it looks around this, that's going to be good enough for me. Now, if you have a peak over here and a peak over here, you're going to lose some points. But something that gives the bell curve shape with the highest point around the mean and tails off, respectively. Once you've got that, you can do some additional things. So you could plot not only the curve, but you could draw lines going up from the standard deviation point up to the curve, and then you can put in there the percentage of data. So I didn't even bother to draw what happens below 1 standard deviation, but we know from -2 to -3 standard deviations, there's 2.1% of the data. From -1 to -2, 13.6. From the mean to 1, it's 34.1. Mean to 1, 34.1. 1 standard deviation above the mean to 2 standard deviations above the mean, 13.6. And 2 standard deviations to 3 standard deviations is 2.1. So there you have it. You've got your normal curve. This is what you are going for when I ask you to draw a normal curve. I'm looking for you to either take or calculate the means and standard deviations, plot them, draw an estimate, and put in there the percentages that fall within that normal curve. And you can do this same thing for any normal or any distribution at all. You get a mean and a standard deviation, you can plot to your heart's content. So let's just go back a little bit in the slide, and you can see, here you go. Make an x-axis, you plot the mean, add the standard deviation to the mean and plot that point, which would be here. And that is 1 standard deviation above the mean. Add another for 2 and 3. Then you take the mean and subtract the standard deviation. That's 1. Do it again for 2 and 3. And then you draw your approximate curve. That's how you draw the curve. All right. That's really about it. When I said that this was going to be a brief lecture, I meant it. These are going to be smaller, shorter amounts of time to cover than when we have the bigger things you're going to be tested over. But remember, you do need this, and this can come up on a variety of things going forward. And this is surprisingly important. Of all the things we do this semester, this actually, especially for people interested in clinical things, like I said, might be the most applicable portion. All right, now if you want to give a shot, you can go ahead and try to solve this problem. If you are confused by it, feel free, come to class and we can go over it there. So what are the goals for you to get from this? Know what a normal curve is, what its properties are, and how to draw it. As of this point, that's good enough for me. All right, and please make sure, as always, bring whatever questions you have to class. I'll have some problems for us to work out, and we should be good to go.